Welcome back, everybody, to INE's CCIE Data Center Nexus switching class. In our next section, we're going to be talking about Overlay Transport Virtualization, or OTV, which is a Layer 2 data center interconnect technology. Now, the first thing we need to know, like the other protocols that we've been talking about during this class, is what is OTV and why would you want to use it? Now, basically, at its core, Overlay Transport Virtualization, or OTV, is essentially just a Layer 2 VPN that is running over IPv4. Now, specifically, OTV is actually an IP or IPv6 over Ethernet, over MPLS, over GRE, over IPv4 tunnel. So essentially, it's an Ethernet over MPLS tunnel that is then encapsulated inside GRE, which is going to allow us to route it over the Layer 3 data center interconnect. So it does add some additional encapsulation overhead. It does not support fragmentation, so we do need to take this into account when we're looking at the amount of overhead that's added from the routing point of view in the Layer 3 header. But the idea here is that since we already have the specification for Ethernet over MPLS, with features like any transport over MPLS or virtual private LAN services, since those are already tried and true and tested mechanisms of doing Layer 2 tunneling, there's really no reason to reinvent the wheel here. Now, additionally, since we are going over any potential transport, and that's one of the advantages here of OTV, is that we're not stuck into certain situations where we must run MPLS or we must have these certain requirements for the interconnect. Basically, as long as we have any IPv4 transport between our sites, could be a dedicated link, could just be over normal internet routing, we are able to run the OTV feature. Now, the reason that we would want to run OTV is that it's mainly designed specifically for the Layer 2 interconnection of data centers, or the Data Center Interconnect, or DCI. Now, we are going to talk about some other potential mechanisms that you could use to connect your data centers, like dark fiber or MPLS type tunnels. But the reason we want to do this in the first place is to allow us to run what's known as virtual machine workload mobility, which essentially means that we have some sort of virtualized resource that we're running in one of our data centers. If there's a failure of the network or the failure of the end host hardware, or just we have an excess resource that we're using, so CPU utilization is too high, the SAN utilization is too high, we can move that workload, or basically move the virtual machine, to different physical resources, and this is going to happen transparently from the end user's perspective. So a good example of this would be what VMware calls their vMotion technology. Basically, it allows the VMware host machines, as long as they have Layer 2 connectivity to each other, they're able to transparently move the virtual machines back and forth between each other. Since we're already using storage that is based on a storage area network, like a fiber channel storage array or fiber channel over Ethernet or iSCSI, of course, those type of details we're going to be talking about in the storage specific class for CCIE Data Center. But all of this is going to fit together towards the overall design of the data center. Now, the reason specifically we would want to use OTV versus some of the other technologies is that there are specific enhancements built in to OTV that are specific to the Layer 2 data center interconnect. So as we talk about the OTV within the scope of other possible tunneling techniques, there's many different options that we could use. Okay, the most basic of these would be dark fiber, whether this is running over coarse wavelength division multiplexing or dense wavelength division multiplexing, the CWDM or the DWDM, which basically means I have a physical fiber, typically a single mode fiber because we're going longer distances, and then we can take multiple optical signals or multiple optical frequencies and wavelengths and then multiplex that over the single physical line. So if I have a single mode fiber, maybe the individual max signal is 10 gigabits. I could be multiplexing that 112 times and get 120 gigabits over the single fiber. Now, we'll see that there are some disadvantages of doing that, of using just dark fiber for the interconnect, and it has to do with the other control plane protocols that are running over the data center interconnect. Now, it's not to say that you can't take dark fiber and then run OTV on top of it. That would be kind of an ideal case because you have a true point-to-point connection that doesn't have other Layer 3 forwarding, so you're not going through like an MPLS provider. So you have the dedicated circuit. Then maybe you have like Layer 1 sonnet protection that's going to give you very high availability, that if there's a physical link cut somewhere in the network, then you're able to do like Layer 1 optical rerouting. But this is just one of the options that we have, basically just a point-to-point link that's dedicated just for our data center traffic. Okay, another option would be some type of tunneling that's going to run over IP, like the Layer 2 Tunneling Protocol version 3, or L2TPv3. Now, the advantage of using L2TPv3 would be that it does not require MPLS in the transit of the core. So you could run L2TPv3 over the internet, as long as you have basic just IP reachability between the devices. It's not necessarily as common as some of the other Layer 2 tunneling techniques, like the Any Transport over MPLS or ATOM feature, or the Virtual Private LAN Services or VPLS feature. Now, ATOM is basically a point-to-point MPLS Layer 2 VPN, while VPLS is a point-to-multipoint Layer 2 MPLS VPN tunnel. The disadvantage of either of these technologies then is that your data center interconnect has to go over an MPLS provider. Now, you can potentially do interoperability where maybe on one data center I have one MPLS provider, on another data center I have a different MPLS provider. There are ways to do inter-AS interoperability, but a lot of times it becomes cost prohibitive, it becomes very design intensive in order to actually allow for this. So these are the traditional type Layer 2 tunnels that you would normally be using like in the enterprise environment, but these may not be the best solutions for our data center interconnect, where we're using it to build a very large Layer 2 topology. Now let's take VPLS for example. One of the potential shortcomings of VPLS is that the service provider edge routers, so the PE routers on the MPLS network side, those must maintain the MAC address table for the customer. Now, in most VPLS designs, this is not an issue, because if we take a look at our whiteboard here, a more typical design that you would have for VPLS would be that you have the service provider core that is running MPLS, then you have the service provider edge routers that are allowing you to do your point-to-multipoint tunnel. So I have 4 PE routers. These would be something like ASRs or GSR or CRS typically. Could also be something like 7600 that's doing our Layer 2 tunneling. And onto the customer side, so we have our customer edge devices here. Typically, these are going to be Layer 3 routers, that they are the demarcation between the Layer 2 domain on the inside of the network and the Layer 3 domain on the outside. So what this means is that basically we would have a different subnet that is from the inside of the CE. So let's say that this is like the 10 network here, and on another site we have the 20 network. On another site we have 30 on the inside, another site we have 40. Then over the service provider core of MPLS, these routers do appear that they are directly connected. So it's basically a full mesh tunnel that looks like a LAN segment, but it's actually a full mesh of pseudo wires. And what we would have in here is some additional segment, let's say 100.0.0.0/24. So these 4 routers appear that like they're on the same LAN segment. Now, for most design cases, this is going to be fine, because the MAC addresses that the provider edge routers on the SP side that they need to maintain in a design like this, there's only going to be 4, because there's only 4 edge routers on the customer side. But in the case of the Layer 2 data center interconnect, that's not what we're trying to accomplish. We're trying to do an end-to-end Layer 2 tunnel, not a demarcation between the Layer 2 internal domain and then the Layer 3, basically Layer 2 over Layer 3 tunnel in the core. So the problem is it becomes not only a scalability issue of what are the MAC addresses that we have in the data center, but then also the service provider has to maintain those. And in most cases, when you buy VPLS service, there will be a limit that the service provider says you cannot send more than this many MAC addresses into the network, because it's their provider edge routers that are going to have to do basically provider backbone bridging in order to allow for that. So VPLS does have its place today still in the network. A lot of times that's what you would use for like Metro Ethernet connections between your maybe local campus buildings in a particular metropolitan area. But in the case of data center interconnect, it's not necessarily the best option, simply because we have a very large Layer 2 flooding domain, a lot of MAC addresses. Okay, we could also theoretically solve this problem just by using normal GRE tunnels. Okay, I could configure a mesh of GRE, I could configure a bridge group, I could put bridging over GRE. So it is going to solve the same type of problem where we're taking our Layer 2 traffic, we're encapsulating it inside layer 3, and then we're sending it over the layer 3 routed data center interconnect. Now, the issue that we're going to run into here, where even though with OTV we actually are using GRE tunnels, there's going to be some additional enhancements that are built into OTV specifically to stop the flooding of things like spanning tree, the ARP requests and replies, the ICMPv6 neighbor discovery request and reply, and also to limit the failure domain if we were to have something like a broadcast storm happen in an individual data center site. So really, at the end of the day, all of these tunneling techniques or the different types of data center interconnect are solving the same problem, where we're trying to get the two data centers to look like they're on the same LAN. Now, again, as I mentioned, with OTV, the specific application that it is designed for is the data center interconnect. You technically can use it for whatever application you want. If you're buying layer 3 service from layer 3 MPLS VPN or maybe just regular layer 3 internet routing, you could configure OTV on top of that, and that's going to allow you to tunnel your layer 2 traffic between your sites. But some of the things specifically for the DCI that OTV is going to build in for us, as I mentioned, it's going to optimize the ARP flooding. One of the things that the edge routers, or what we call the authoritative edge devices in OTV, is that they will have a proxy ARP cache in order to respond to local ARP requests for destinations that are reachable over the data center interconnect. So something like VPLS or any transport over MPLS, they do not have a feature built in like that. So it means that all the ARP requests in the entire network, it's automatically always going to be going over the DCI if you were to use MPLS. So ideally, we want to keep just our data plane traffic over the OTV tunnel or the data center interconnect. We don't want to expand the control plane to a very large environment, because then we just run into scalability issues of things like spanning tree or just the end-to-end MAC address table for the switches that we're using. So as I mentioned here, OTV is going to be the demarcation point of the spanning tree domain. So even though we can use it to span the same layer 2 segment, like the same layer 2 VLAN between the different data center sites, it does not automatically mean that they're going to be in the same spanning tree domain. Now, the other thing that OTV is really helpful with is when we're trying to do the overlay of multiple VLANs. Now, in the case of something like VPLS, you technically can tunnel multiple VLANs. So I could say I have VLANs 10, 20, 30, 40 on one side, and I want them to appear the same, 10, 20, 30, 40 on the other side. But we run into some limitations of what the provider edge routers on the SP side need to do in order to allow this. So we could have basically 4 different sets of VPLS tunnels or pseudo wires to allow us to have VLANs 10, 20, 30, 40. We could possibly do some sort of .1Q tunneling technique, but at the end of the day, it's really not designed to do that. You can kind of hack the process to get it to work, but it wasn't originally designed to do that. It's basically meant to emulate just a single LAN on the outside. You put your routers around the edge, and then you have your own demarcation between layer 2 and layer 3 to prevent like the MAC address flooding and ARP flooding. Okay, the other thing that OTV is going to give us is multiple edge routers without overcomplicating the design. MPLS is not going to allow you to do this. You would have to have separate routers that have separate MPLS circuits for layer 2, so separate VPLS tunnels or separate any transport over MPLS tunnels, and there are no loop prevention mechanisms really built into those protocols. So you could potentially configure 2 circuits, but then you're going to have to run spanning tree on top of it in order to make sure that one of them is actively forwarding, one of them is standby, and that's not really what we want. We ideally want active forwarding for any of our interconnects. So as we start to explore this on the command line and go through some different configuration and verification examples, it'll make a little bit more sense why you would want to choose OTV over these other techniques that you could use for the interconnect. So the next thing we need to know then are what are the specific terms in OTV and what do they really mean when we're talking about the control plane behind the scenes and then the actual data plane forwarding. And the first of which is the OTV edge device. So this is the basically layer 3 device that's actually going to be running the OTV feature set. In our case, this is going to be Nexus 7000. It is also supported on ASR 1000, and it's going to be supported on other platforms later down the road. So this is where we actually have the tunnel that we're taking the layer 2 traffic, encapsulating it inside GRE, actually Ethernet over MPLS over GRE, then sending it across the layer 3 routed network It's going to come out on the other side and then get decapsulated back into layer 2. Now, of these edge routers, we can actually have multiples of them. So we have not only the edge device, but we have what's known as the authoritative edge device, or the AED. Now, the AED is going to be used in any time when we have multiple edge routers for the purpose of redundancy, and we want to make sure that we have some load distribution between the two of them. So the AED is going to be essentially the active forwarder on a per VLAN basis that the OTV tunnel is trying to send the traffic across. So let's say, for example, I have my interconnect and I have 4 VLANs. I have VLANs 10, 20, 30, and 40 that I'm trying to essentially bridge over layer 3. If we were to have 2 authoritative edge devices, 2 AEDs, one of them is going to be elected the forwarder for 2 of the VLANs, the other one is going to be elected the forwarder for the other 2 VLANs. Now, as it stands right now in the current revisions of codes, this is not really something that you configure. We do some kind of crude load balancing just by saying this AED is going to be elected for the odd VLANs, the other AED is going to be elected for the even VLANs. So that does play into your overall design. Now, what I mean by this, let's say that we have some very bandwidth-hungry applications that are all on even VLANs, like 10, 20, 40, 60, 80, etc. Okay, this means that the same edge device will be elected for forwarding of these, and if we don't have any odd VLANs used for traffic, 10, 30, 50, etc., then the other edge router is not going to be used. So the actual numbering now that you're using for the VLANs is going to have an effect on how the traffic is forwarded over the DCI, over the data center interconnect. Now the key here is that since we have multiple edge routers, we need to make sure that we have some loop prevention techniques built in. So we'll see that once we configure OTV with multiple edge routers, there's going to be an election for the AEDs, and that's going to make sure that neither of them are forwarding in an active state for a particular VLAN. Because since we are not extending spanning tree over the DCI, we have no additional layer 2 loop prevention technique. So again, the way that we're doing this is by basically saying only one router can actively forward a VLAN at a time. And then we're doing, again, the per VLAN load distribution between the edge devices, between the AEDs. Okay, next we have what's known as the extend VLAN. The extend VLAN is basically the layer 2 segment that we're trying to bridge over OTV, or we're trying to tunnel over OTV. We then have the site VLAN. The site VLAN is going to be used for the AED election. So the site VLAN is going to be something that is not spanned over OTV. This was something specifically when we configure it, it is not going to be allowed on the overlay interface. So the site VLAN is just internal for the 2 edge routers to talk to each other, similar to how you would think of like the peer link in VPC. So it's for synchronizing the control plane between the 2 of them. Okay, next we have the OTV site identifier. This is used as a basic loop prevention technique to make sure that if a packet were to go out and to come back in, I'm not going to receive my own packet since I'm part of that same site. So when we're configuring this, we need to make sure that it's a unique identifier per site. And if we have more than one AED, so we have more than one edge router, we want to make sure that they're using the same site identifier. So they know that they should perform the election and then say, I'm going to forward VLANs 1, 3, 5, 7. You're going to forward VLANs 2, 4, 6, 8. We then have the overlay interface. This is the equivalent of our GRE tunnel interface. So this is the logical link that is going to be used for the tunneling. And then, of course, we have the physical link that the tunnel is going to run on top of. This is what we call the OTV join interface. So the join interface is going to be the physical link or the port channel that is used to route upstream towards the data center interconnect. And as it stands with current versions, the join interface cannot be an SVI. So it has to be either a physical link or a port channel, and that would be a layer 3 port channel because that's what we're using to route upstream towards the DCI. We then have 2 multicast groups for OTV. One is called the OTV control group. Now this is going to be used for extending the control plane protocols like ARP or OSPF or EIGRP over the data center interconnect. And this traffic is going to be tunneled inside of multicast over the DCI network. So this is then implying that by default, your transit, if you're using like MPLS Layer 3 VPN, it does have to be multicast aware. It does have to support both any source multicast ASM and source-specific multicast SSM. We have the second group called the OTV data group. This is when we're going to be actually tunneling multicast between the sites, so multicast in the data plane. So if I have multicast video feeds that are going between my data centers, this is going to get encapsulated inside multicast so we can avoid what's known as head-end replication, or basically taking a multicast packet and not having to make multiple unicast copies of it in order to forward it over the DCI. So we'll take a look at some cases where we need multicast for OTV, which is going to be the default behavior, and then something that's known as the OTV adjacency server that we can use to tunnel everything over unicast and then not need this multicast requirement for the transit network. But the key here is that by default you do need to have a multicast-aware transit network between the AEDs. Now, we already talked about up to this point Fabric Path and how Fabric Path uses IS to IS in its control plane to exchange the switch IDs and to build the shortest path tree in order for us to do our MAC in MAC routing, or basically our layer 2 IS to IS routing. Now, OTV is actually going to use a similar logic to this, that it's going to be using IS to IS to exchange the control plane. There's a key difference between them, though, and that IS to IS for OTV is actually used to advertise the MAC addresses of the end hosts. In the case of Fabric Path, IS to IS is only used to build the shortest path tree between these switch IDs. Then we use normal MAC address flooding in order for the devices in the core to be able to actually switch the data plane. But with OTV, this is going to be an event-driven behavior that the edge routers, the authoritative edge devices, they are only going to know the MAC addresses that are actively advertised with IS to IS. Now, the advantage of doing this is that it's going to give us more control as to what specific types of traffic can be sent over OTV. Where in the case of something like MPLS L2 VPN, we would apply a layer 3 access list to the interface or maybe some sort of VLAN access list in order to stop the traffic from flowing across the link. In the case of OTV, we can stop this in the control plane by telling IS to IS not to advertise specific MAC addresses. So if I have an individual host that I wanted to stay local and not go over DCI, I could deny that from being advertised in the IS-IS control plane. So we could think of it kind of like a distribute list that's applied to layer 2 MAC addresses inside of the IS-IS advertisements. So as we compare some of the terminology between Fabric Path and OTV, Fabric Path is considered MAC in MAC routing because we're taking our Ethernet frame and then encapsulating it inside of Fabric Path. In the case of OTV, we're taking our layer 2 Ethernet and we're encapsulating it inside of IP, where again it's actually Ethernet over MPLS, over GRE, over IP. So it's considered MAC in IP routing. Now, the control group multicast, as I mentioned, for OTV is then going to be needed to exchange the IS-IS control plane. Specifically, IS-IS, again, it does not have its, it does have its own layer 3 transport, so it doesn't need IP to get from one point to the other point. Okay, so this means that if I were to have the AEDs, the edge devices on the data center edge, and I want them to be IS-IS adjacent, I'm going to have some problems considering that the transit network between them is IPv4. Because IS-IS does not run over IP, it runs over its own CLNS or CLNP stack. So in order to allow us to do this, the control plane of IS-IS is encapsulated inside Ethernet over MPLS over GRE inside IPv4 multicast. So again, what this means is that in the core of the data center interconnect, it must be any source multicast aware, or basically allowed shared trees, which means we would have a rendezvous point either in normal sparse mode or a rendezvous point in bidirectional mode. Now we'll see there are some workarounds for this. We can encapsulate IS-IS inside of unicast if we're using the adjacency server, and that's going to remove the requirement that the core of the DCI network be layer 3 multicast routing aware. The next portion, of course, then is going to be the data plane. So once we figure out who are the edge devices in the network, what are the MAC addresses that they're using, how do we actually forward the traffic between the sites? Now the key here is that we're going to be using both multicast and unicast for transport. And I'm talking about IP version 4 here is going to be the transport. Now for multicast, we have the first multicast control group, which is going to be used for any type of multicast control plane protocols like OSPF or EIGRP or PIM that we're trying to tunnel over OTV. And it can be used for broadcast, so things like our address resolution protocol. That would be tunneled inside the multicast control plane group or the multicast control group. We then have our normal unicast data, like our database replication or web browsing or whatever normal unicast data we have. That's going to be encapsulated as normal unicast traffic between the edge routers. So again, specifically, it is our IPv4 or IPv6, whatever the application is, over Ethernet, over MPLS, over GRE, then in this case over IPv4 unicast. Then we have the potential for actual multicast data flows. This would be like our video on demand or something like that. In this case, the multicast is going to be encapsulated as source-specific multicast, as SSM. So this then additionally implies that the authoritative edge devices, or the AEDs, they must be using IGMP version 3 in order to generate the source-specific joins, or the S-G joins, in order to get us on the shortest path tree for the particular remote sender. So we're going to go through this looking at the OTV configuration on the edge. We'll look at what actually happened in the core of the DCI, look at what type of traffic is running as the multicast control plane group, what is running as the multicast data plane group, and then what is running as the regular unicast data plane. Then we'll look at the configuration of using the adjacency server, which is essentially going to remove the requirement for a multicast. But in the case that we have more than 2 data centers that we are connecting over the DCI, we would not want to use this. So ideally, you would have a multicast-aware layer 3 transit, which means that your control plane and your actual multicast data plane is going to be efficiently transported. But in the case that you don't have layer 3 PIM in the middle of the network, you can use the adjacency server, but it could end up in some additional replication. So let's say, for example, our particular data center application is like triple play service for video, where we have like our voice video traffic that's running over the voice video and internet traffic running over the data center. If we have HD video streams that are moving between the data center sites, and I have 3 or more data center sites, I would have to take those streams and re-encapsulate them in a unicast multiple times in order to get over the data center interconnect. So it's kind of like these legacy problems that we had many years ago with frame relay hub and spoke networks. That is, we're trying to send multicast or broadcast traffic over a non-broadcast network. We would have to do what's known as pseudo-broadcast or replicated unicast to take the multicast or broadcast packet and actually make multiple layer 2 unicast copies. Where in this case, the adjacency server is forcing us to do multiple layer 3 unicast copies. But in the case that you only have 2 data center sites, it's not going to be an issue because it's always point-to-point unicast between the neighbors. Now, as I mentioned, there are going to be some specific optimizations for OTV, and some of the reasons why you would want to run OTV as the DCI solution as opposed to like layer 2 MPLS tunnels. Okay, the first of them is going to be that the other options are going to bridge all traffic. So without some extensive manual filtering of things like ARP or different layer 2 protocols like spanning tree, those are normally going to be automatically going across the layer 2 tunnels. So like in the case of a point-to-point ATOM tunnel, the any transport over MPLS, a layer 2 pseudo wire, that is not going to stop spanning tree, or it's not going to stop broadcast storms. OTV is going to fix this by having the edge routers run the proxy ARP and the proxy ICMP neighbor discovery cache, and it's also going to be terminating the spanning tree domain locally on the edge router. So let's go ahead and take a look at the topology that we're going to be using for these examples. And we essentially have all of the 7Ks here. We have 8 different VDCs that we're going to be using to establish the OTV tunnels between. And there's a couple hardware requirements that we need to talk about here first. Now, in the current NXOS releases on the Nexus 7K, there are some incompatibilities between OTV and other features. Okay, the most notable one is that you cannot run OTV inside the same VDC that you have layer 3 SVIs. So this is actually a pretty big limitation here, Because normally we're going to have our layer 3 VLAN interfaces where we are running our first hop redundancy protocols, like HSRP, VRRP, or GLBP. For the virtual device context that we have that configuration in, OTV is not going to work. There's some technical limitation behind the scenes of how the tunneling is actually implemented, and we're not actually able to do the encapsulation. So we essentially need a separate dedicated VDC to run the OTV process. So there's a couple different designs that you could do with this. You could have a different physical box that's used for OTV, or you could do kind of VDC on a stick where you route out to it and then back. As long as the OTV process is separated from the rest of the layer 3 routing, really that's what we need to be aware of. So in this particular design, if we look back at the diagram here, we're going to have the two 7Ks that are essentially on the same layer 2 segments as our server 1 and as our router 3. Now we know from the previous physical topology that we actually have some 5Ks in here, that we actually have some 2Ks in here. But from the design point of view of OTV, that's really outside the scope. As long as we have layer 2 reachability up to the edge routers, up to the AEDs, that's all that OTV cares about. Doesn't care if you're running VPC, if you're doing fabric path even, you can get the traffic up to the layer 2 edge, then we're going to encapsulate it inside the layer 3 tunnel. So first we're going to look at here doing OTV just between two devices. So we'll say that we have our layer 3 domain that is going to get us up to, or I should say our layer 2 domain, that is going to get us up to this edge router. So we'll say Nexus 7K1-3, this is going to be our first authoritative edge device. Then we're going to have, in the middle of the network, this is basically the DCI. This is our layer 3 data center interconnect. So over Nexus 7K14 and Nexus 7K25, we're going to be running routing. We could do IGP, we could do BGP, as long as we have layer 3 connectivity between the AEDs. That's really what we care about here. Okay, then we're going to have the other edge router on the other side, which is N7K2-6. So this is our AED here. It means that the layer 3 tunnel is essentially going to be between these devices. So again, this is our Ethernet over MPLS, over GRE, over IPv4 unicast and IPv4 multicast. So this additional encapsulation overhead, you do need to take it into account when you are looking at your actual applications, because OTV edge devices do not support layer 3 fragmentation. So it means you have to offload that down to your actual end machines. So you would want to lower, if you're using Jumbo MTU and your DCI supports Jumbo MTU, you would want to lower it on the end machines maybe down to 8,000 something. So it's not a lot of overhead, and we're going to look at this specifically, the exact packet structure. It's not a lot of overhead, but it is something that you do need to take into account there. Okay, there's a couple questions we have here. My service provider should allow multicast, or is it allowed by default? It is not allowed by default. So when you're buying layer 3 transit service, that's going to be one of the options that generally you're going to have to pay extra for. That you normally don't get multicast service, you have to specifically buy that. Okay, also in the case of MPLS layer 3 VPNs. Normally when you're looking at your service contract with them, your service level agreement, that's going to be one of the line items. Do you support multicast? How do you support multicast? Am I going to have to use my own rendezvous point? Am I going to use your rendezvous point? Am I going to use static RP? Am I going to use BID, or am I going to use BSR? That's all part of the agreement between the service provider and the customer. Because in the case that you're using MPLS L3 VPN, you will be exchanging layer 3 routing updates with the service provider. Typically BGP between the provider edge and customer edge, but it technically could also be an IGP like OSPF or EIGRP. So typically, no, multicast is not allowed by default. There's a question, I'd understood that you can't have SVIs in the OTV VDC. That is true. Shortly, you'll be able to use a loopback for the join interface. Okay, that I did read that in some of the release notes. That's one of the features that they're adding, which basically makes it a little bit more independent of what your layer 3 infrastructure routing northbound is towards the DCI. Because right now, again, the limitation is that it has to be on a native layer 3 routed interface or a native layer 3 routed port channel. So it's not supported on an SVI, it's not supported on a loopback, where you would think of like in the case of BGP, or in the case of like a normal GRE tunnel, you could set the update source to your loopback, or you could set the tunnel source to your loopback. But with the current code revisions, that's not a supported feature for OTV. There's a question, can your layer 3 DCI devices be virtual off the core 7K? Can your layer 3 DCI devices be virtual off the core 7K? Do you mean the device that's doing the OTV encapsulation? So that's actually running the OTV feature set? So OTV can run in a VDC, and that's what we're going to be doing here, because we have two physical boxes. We have Nexus 7K1 and Nexus 7K2. These two physical boxes are then split into 4 VDCs each. So the issue is that we can't run it inside the same VDC that we're doing the SVI routing. Like Nexus 7K1 and 2 are now. Can your layer 3 DCI device be a virtual device off of the core? What you could do is you could have a case like this, where this could be your, so let's say this guy is over here, and the layer 3 uplinks, let's say the layer 3 network goes like that. What you can do is send the traffic out and then back in and have this one run OTV. This is basically like VDC on a stick. So you're routing out and then back in. Then your physical routing towards the uplinks are going this direction. Okay, there's also one other requirement that I forgot to mention. You cannot do this on F1 cards, because again, F1 is our layer 2. You need the layer 3 M modules in order to do OTV. So the edge ports that are facing upstream, which is going to be not the overlay interface, but our join interface, that's going to have to be on the M1 module. There's a question, will OTV run over older SONET type point-to-point circuits, or is an underlying MPLS a requirement? Okay, yes, it will actually run over anything, and that's one of the design advantages of OTV. As long as you have any type of IPv4 reachability, you can use any circuits that you want. So you could use legacy DS3, you could use OC3 SONET, OC12 SONET, you could use point-to-point 10 gig E or point-to-point OC768. It's really up to you for the physical circuit. The only requirement is that you're basically able to ping between the edge routers, that you have basic IPv4 reachability. Now, when we compare that to some of the other techniques like ATOM or VPLS, those are not transport agnostic, or basically means they do require specific transports. And in that case, it means that for ATOM and VPLS, they do require that you're running MPLS in the core of the service provider. So basically, the idea of OTV is that you have a data center in Los Angeles, you have a data center in New York. You may not have the same service provider that you can buy the same service between. So for whatever your long haul link is, you can run whatever you want. You could just route it over the internet. Of course, you're probably not going to get the greatest service level agreement if you just route it over the internet. But essentially, any layer 3 connection, that's all that is the requirement for OTV. There's a question, is OTV Cisco proprietary? It actually is right now, but it is not going to be. There is a standards track version of it, and let me open that up, which is, we search for the OTV RFC. It is Overlay Transport Virtualization, currently still in draft. This most recent version, version 3, right now it's expired, so there should be another version that's coming out shortly. One thing that's kind of notable about this, if you read through the RFC specifics and we look at the encapsulation of the data plane, it says that the format of OTV is for UDP IPv4 encapsulation. This is what the standards track says, but this is not actually what Cisco is implementing it as. Cisco is implementing it as Ethernet over MPLS over GRE, over IPv4. So it's not encapsulated in UDP, it's encapsulated in MPLS over GRE. So most likely the next revision that comes out is going to update this, because it wouldn't make sense to write a standardized implementation that says use UDP And then Cisco's implementation uses GRE, and then of course those two would not be interoperable. So right now it's Cisco proprietary, but it is on standards track. Okay, there's a question, just to make sure I understand this, if I only have 2 DCs, I can run OTV without multicast. That is correct. Okay, you can run it without multicast if you have more than 2 DCs. So you could do 3, 4, 5. It just means that your replication of the traffic is not going to be as efficient as it would be if you had multicast. Okay, really it only matters if you're running multicast in the data plane. If you don't have any multicast applications, then you really don't need multicast in the core. Just means that for some of the control plane stuff like your ISIS advertisements or your ARP flooding or some of your MAC flooding, that would have to use unicast replication, but that's going to be a much smaller amount of your transfer versus like your actual UDP multicast data flows. So like if you're running HD video, if you're a video on demand provider, that's going to be a big deal because you generally have a couple hundred channels, each of them maybe, 15 megabits per second or something for HD. So it's going to start to add up quickly the amount of traffic that you would have to replicate over and over for the multicast. There's a question, how about layer 3 addressing will fall in with OTV between the 2 data centers? Do both data centers have to share IP addressing and VLANs for the few VLANs? They do. So the goal of what we're trying to accomplish is that we're doing layer 2 tunneling. So if we look back at our diagram here, the end result is that router 3 is going to have the address 10.0.0.3, and router 2 is going to have the address 10.0.0.2. We're going to have VLAN 10 on this side. We're going to have VLAN 10 on this side. And it's the same broadcast domain end to end. So these devices will not have to route to reach each other. From their perspective, they're going to look like they're connected on the layer 2 LAN. And the reason why we're doing it that way is that the virtual machine mobility applications require it. So when you're doing like VMware vMotion, it is a requirement that you have your VMware hosts on the same subnet. So they have to have layer 2 connectivity in order to do the like the live vMotion between them. So we can do layer 3 routing, but that's kind of outside the scope of the OTV config.